um, or rather ionization energy. Okay, or basically, you know the definition. Ionization energy is the minimum amount of energy that is required to remove 1 mole of electron from the outermost shell of a gaseous atom to become a partially positive ion. Okay, to become a positively charged ion. So I'm saying that again. It's the minimum amount of energy required to remove 1 mole of electron from the outermost shell of a gaseous atom. You have to put that from the outermost shell of a gaseous atom in order to become a positively charged atom. Okay, so when you remove this, it becomes this. That's what that implies. Now that's ionization energy. Now there are three main factors that affect ionization energy. The first factor there is the first factor of all of them is the atomic radius. The second one is the nuclear charge. You can call it the proton number. And the third one is the shielding effect. Okay, the shielding effect. So the three of them are a big factor in determining the nature of the ionization energy of an element. Now, what do we expect to see? What is expected? What's the expected value for? What's the expected trend of ionization energy across the period and down the group? Now, typically, it will be sensible to think of it as we expect that ionization energy increases from left to right across the period and decreases down the group. Okay. Now, what do I mean by that? What I mean by that is this. You can see the chart on the screen. This one is the ionization energy of the period 1 and 2. Okay, because this one is in period 1, this is in period 1, these are in period 2. Okay, this is in period 2 and this is in period 3. So now what do we expect to see? Now typically we expect that the ionization energy should increase. Okay, we expect that ionization energy should increase across the period and down the group. Okay, what do I mean by that? Now if we have hydrogen with only one element, only one electron, it will be relatively easy to remove it. Okay, compared to when I have two, I'll use energy to remove these two. Compared when I have three, I use more energy to use three. So expectedly, we expect it to increase from left to right across the period. That is the expected norm. Okay, but most times it doesn't happen like that, and that's why we have this chart on the screen. So I want to explain why does it not happen? What are the exceptions? You see, those are the things they can ask you. What are the exceptions to this rule? Why is the ionization of energy of something not greater or not smaller? Okay. Now let's try to observe the anomalies, the abnormal thing. Now, this going up is normal, is expected. Now coming down is not expected. Okay, we expect that it's going to go up from something to something. So why does it come down? Is not an expected behavior. It's not an expected behavior. We're going to explain. So the first thing we want to explain is why is it that the ionization energy of helium is greater than that of lithium? Why is it not the other way around? That's the first abnormal situation we observe. The second one is if you look at beryllium and boron, that's also another abnormal. It's supposed to be beryllium, they're supposed to go up to boron. So that means beryllium again is greater than boron. That's another abnormal situation. The next one is nitrogen and oxygen. Okay, nitrogen is greater than oxygen. I'll have to take it off. So I have helium. Greater than lithium. I have beryllium greater than boron. I have nitrogen greater than oxygen. Okay, and I have neons greater than sodium. That one is expected. Okay, but I'm still going to explain that. Neon greater than sodium. So let's try to explain each one and why do you think all this abnormal situation happens. Okay, let's start with the first one. What's the structure? What's the electronic configuration of this? This one is 1s2. Now this one is 1s2, 2s1. Okay, there is something called electron. I told there are three factors affecting the rate of ionization energy. The first one is the shielding effect. The atomic radius or radius of the atom, shielding effect, and of course the nuclear charge, which we call the proton number. So one at times can win over the other. So let's try to understand the first situation. You can see that the first one has only one suborbital, okay, something like this, and the electrons will spin in opposite direction, okay. But the second one has two orbitals, okay. This one would go for lithium. This one only is for helium. So you would expect that to remove electron from this outside will be easy than removing from this inside. You would agree with that, okay? What I mean by that is that I'm going to clean the screen and take them one by one. Helium. Now, helium is greater because it's greater than lithium because it will take more energy. This one has just the shell. This one have two, one and two, okay? And this one will be like this will be like 1, 2, then 3. So it will be easy to take away the one that is standing outside here. It will be convenient taking away that one. It will be convenient taking away this than taking from here, okay? Because um typically the proton, if we look at the proton number, we expect that the lithium has a higher proton number than helium, but because the electron that is left is outside, is the only one outside the 2s orbital, so the shielding, that means the pushing effect of the two electron inside is greater on one. It's like two person is pushing one person now, so the shielding effect on the external or the outside electron in the 2s orbital is greater. So that means it would, and when there is increase in shielding effect, there is lower ionization energy. Okay, in a literary sense, what I mean is that when there is increase in the shielding effect, when the pushing is high, then we can push it away. Okay, when the pushing is high, that means when the shielding is greater, then we can push it away, meaning that it can lose the electron. Okay, so it will be easy for me to take away look at a very unfortunate situation, a kidnapping situation. Okay, it is difficult to kidnap a man or a boy or a child inside his own house. It will take a very great effort to do that. But it is convenient to kidnap a child that is walking lonely on the streets at night. You get that? So it's a similar thing here. The electron here is alone, and the two electron inside is pushing it outside, and that is shielding effect, and that means to remove that electron is easier. I'll use less energy, and that is why that one is the first case. So the helium and lithium is because there is a great shielding effect by the internal electron, this 1s electron, on the 2s electron. Okay, that causes the low ionization energy. So let's explain why the second one. I'm going to take this off. Let's explain why we have anomaly in boron, and beryllium. Okay, what do we have anomaly? So let's write them out. Beryllium, what's that? 1s2, 2s2. Okay, boron, 1s2, 2s2, 2p1. You could already have known the answer already. Okay, now we expect, of course, that the let's look at, because the question here is that boron is expected to have a higher ionization energy. Now it has a lower ionization energy. So we want to look at which one causes the ionization energy of this one to be lower. But you would have already seen the relationship between the first explanation I give and the second one. Remember when I did helium? Helium was 1s2. Is it lithium? Lithium was 1s2, 2s1. You see, one is outside, one is outside. Two is inside, two is inside. So you see the relationship already. So the explanation that I give for beryllium and boron is the same explanation we are giving for this one. So it's still the shielding effect that pushes away the lone pair electron and makes the ionization energy of that element to reduce. Okay, I think you get that. So let's go to the third anomaly. The third anomaly, okay, I put down the information here also, but I want to use this chart. It's easier using this than the other one. Now, we have explained the anomaly of this. We have explained the anomaly of this. Now we want to explain the anomaly of this. But let's see if the same explanation will go or different. So let's draw the structure of nitrogen. The structure of nitrogen is 1s2 because nitrogen is 7, remember? So we're going to have 1s2, 2s2, 2p 2p we need 7, now 2p3, okay? Now this is nitrogen. So oxygen is 8, so that would be 1s2, 2s2, 2p 4 this time around, okay? Now this is oxygen. So I'm going to clean the screen and try to write them again so that I can have space for nitrogen. Sorry, the application I'm using is not nitrogen. I'm going to draw the shape 1s2, 2s2, 2p3. So I'm going to draw the 2p3. Okay, I'm just going to put 2 inside. You know what that means. 2p3 is going to enter singly. Okay, now the oxygen is 1s2, 2s2, 2p4. So 2p4 would be 1, 2, 3, then 4. Okay, this one are the same thing. Now I want to explain why is it that we have a lower oxidation ionization energy in oxygen than hydrogen. So let's look at it. What explanation can we give that the that the oxidation number of oxygen is lower than uh, nitrogen? Okay, good. Now let's look at it together. There's something called electron repulsion, okay, or shielding. Shielding is different from electron repulsion, okay. Shielding is a cloudy situation. I want to explain the difference. Now, if you have this situation, let's say this is the outermost shell, and we have another shell, innermost shell. Now, if I have 8 electrons here, okay, and I have 2 outside, and I have another 2 inside, of course. Now, this will be 2, 8, 1, so we can think of sodium. Now, what we call shielding is the repulsion, the general repulsion, the group repulsion, like the coordinate repulsion of all these electrons. When all these electrons are pushing away these 2 electrons, we call it shielding effect. So the repulsion between the innermost electron and the outermost electron is called shielding effect. That is shielding. But there is also a repulsion between these 2. Electrons are negatively charged, remember? And like charges will always repel each other. So there is also a repulsion between the electrons outside. So that one is not shielding effect. We only call it repulsion. You can call it electron repulsion. Okay? So what I'm about to explain is about the electron repulsion, not shielding effect. Okay? You get that clear? Good. Now back to the explanation. Let's start with this. The repulsion in this one and the repulsion in this one, which one do you think will be greater? Common sense. There are 3 persons pushing each other here. There are 4 persons pushing each other here. There will be more trouble here than here. So I expect that there is less electron repulsion here, and there is more electron repulsion here. Okay, there is less electron repulsion here, and there is more electron repulsion here. It implies that the increased electron repulsion in the 2p x, 2py, and 2pz orbital of oxygen reduces It's oxidation, it's ionization energy. And you remember what I told you about repulsion? It's like I am sending away these four and I'm sending away three. Okay? If somebody wants to kidnap someone, if three persons are going in a bush and another bush, four persons are going, and the four of them they do not agree. Okay? The four of them they do not agree. So they stay far apart. The three of them do not agree, but their distance between them is not too large. So it is easy to take away from the four that stay far apart and do not agree than to take away from three that stays closer even though they do not agree. So what I'm trying to say is that if you look at this situation, you can see that um, it will be easy to take away from oxygen. That means I'll use lesser ionization energy than compare with nitrogen. So that explains, in a nutshell, it implies that the difference in the ionization energy, the anomaly, is because the repulsion of the electrons in the 2p orbitals is greater than that of repulsion of electrons in the 2p orbitals of the nitrogen. Okay, that explains that one. And from neon to sodium, that's a simple technique to use. If you look at neon to sodium, let me take this off. If you look at neon to sodium, it is expected. So let's try to draw the structure. Neon is 1s2, 2s2, 2p6, 3s2. Oh no, that's everything. It's not 3s2. Okay, it ends here. Now, sodium is 1s2, 2s2, 2p6, 3s1. Now, it is expected because you know that just the same theory we explained in the first one, the way I explained the hydrogen and lithium, is the same way you're going to explain neon and sodium. Okay, the same way you're going to explain them, in the sense that neon and sodium are in different periods. Okay, are in different periods. So it is expected that the atomic radius of neon is how will I put it, is relatively bigger than that of sodium. I have to mention that the when you have atomic radius, it goes down the group. Okay, atomic radius reduce like this and increase down. Okay, it reduce like this and increase down. But the issue is that the element, the electron in the atomic shell of sodium, which is 1, is found in the s orbital, and all the inside are filled up. So the shielding, the pushing on the 3s is greater than the s, because the 3s is even standing alone. Remember the same explanation I gave for helium and lithium, that the lithium have its only one electron in the atomic shell and it is being shielded by two electrons. Here too, sodium have electron in the atomic shell which is 1 and it is being shielded by 10 different electrons. Can you imagine that? So the push on the one electron is greater than the attraction to the nucleus. So that means it is expected to have a lower ionization energy. Okay, I believe that's clear enough. So that explains the anomaly, why this one is this, why this one is that. And you could see that I summarized it here. I said, why is IE of B less than E? You see? And why is IE of O less than N? So you could already go back to the explanation and use that. Now, why is IE increasing across the period? You can give a simple example to that. Normally, we expect it to increase across the period because there is increase in proton number or nuclear charge. And when there is increase in nuclear charge, there will be increase in nuclear attraction, atomic radius will reduce, and ionization energy would increase. I'll put that again. Why do IE increase across the period? There is increase in nuclear charge, which is proton number. There is therefore reduction in atomic radius. When there is increase in nuclear charge, the atomic radius will reduce. Okay, that means what I'm saying in a literal sense is that when you have something like this and the person that is pushing on this thing is increasing, so expect it to push more downward expectedly. That's what I mean by reducing in atomic radius. So when I said the increase in nuclear charge increases the atomic radius and ionization energy increases. But why does it decrease than decrease? Just opposite of this. Okay, just go with opposite of this. the the only thing is that you don't say there is decrease in nuclear. No, the explanation for why it decreases and decreases is because there is increase in the number of shell. Okay, there's increase in the number of shell. Why does it increase down the group? There's increase in the number of shell. Okay, there's increase in the number of shell. Therefore, the atomic radius increases, and therefore ionization energy increases. Yeah, ionization energy decreases. Sorry, not increases. I'll say that again. I said down the group. Why does it decrease? There is increase in the number of shell. Number one. Number two, the nuclear attraction reduces. Number two. Number three, the ionization energy reduces. You can put it that way. Or you can decide to explain in terms of atomic radius. You can say there is increase in atomic radius. Okay, that means that the element increases in size. That means if there is increase in atomic radius, ionization energy will reduce. Atomic radius and ionization energy, they're opposite in function. Okay, that's very important to take note. I think that answers all these questions. So, I have done this for you. Now, what I want us to do now is to use certain information to infer. You can use the information of the ionization energy to predict the element. Now, look at this shape. I want to predict this element. Now, this is the ionization energy. This is not a complete chart, okay? I only sketch it. I think I have other charts. So this is number 1, 2, 3, 4, 5, 6. They'll put electrons here, and they'll put ionization energy, okay? Something like that. Now, you would notice, remember, ionization energy is the minimum amount of energy required to remove 1 mole of an electron from the atom shell of a gaseous atom to form a positively charged atom. Okay. Now, what I'm trying to say here is that if I want to remove one element, if I want to remove the first element, the first electron, pardon me, the first electron, okay, I would need lesser energy, okay, and that's this. If I want to remove the second one, well, I'll need relatively greater energy than the first one, which is understandable. If I want to remove the third one, I'll still need a relatively greater energy than the second, which is fine. If I want to remove the fourth one, well, it is understandable that I have a reasonable little greater energy than the third one, which is still understandable. But look at this peak. It jumps from the fourth one to a very high ionization energy. So it implies something is odd about that peak. That's the peak you have to check. Okay, it's very, very important to check that peak. So the first thing I want to tell you is that because I remove 4 electrons before I have a long peak, it means that my element in question must have 4 electrons in the atom shell. That is why it is easy to remove these 4. But the fifth one is difficult to remove because it is inside. So that means my elements have at least 2 shells. But I want to find out the 2 shells that it has. Is that everything? Does it have just 2 shells or what? Let me find out. Now, after you remove this, now again, also remove another one. But it takes a reasonable amount of energy to remove it again. So it tells me that I already know my elements have 4 electrons in the atom shell. So it's in group 4. That's the first thing. It's in group 4. But I don't know which element in group 4. I want to know the period now. The period is the number of shells that I can count. Now, this one here, the first boundary here, let me take it off. The first boundary here is for shell 1. This one is most likely another shell. Okay, it's most likely another shell. Now, because they did not tell me that this is the end of all the electron, okay? They did not tell me that that's the end. So they only show 6 out of the whole of the electron. So that means it still remain more electron. If you remember electronic configuration, if I write 2,4, it tells you that this element is in group 2 period 4. Is in group 4 period 2. Is in group 4 period 2. That's the meaning of 2,4. And it tells me that there is no way I can remove another electron because there are 6 electrons. But in this one, they do not tell me in the chart. You see the chart I'm going to show you again. They do not say this is the last one. So they only draw 6 electrons. So probably there is more to it. There is definitely going to be more to it. Okay, there's definitely going to be more to it. So it implies that there must be another element electron here. There must be another electron here. It implies that it has more than one electron, and there is only one. There is only one possibility that can happen. It implies that after it has 4 outside, there must be 8 inside. Then there must be another 2 outside. Because if I remove these 2 and I can still get another electron, that means what is left here is not 2, it's greater than 2. And there is no way you can have something that is less than 8. Okay, you remember after 2 you write 8. You cannot have 2, 4, 4. It's not possible. So it has to be 2 something 4. So it implies that the 8 in question is from where I remove these 2. So it still remains like 6 different electrons. Okay, because the reason I say that is because the distance, let me show you another key. The distance between these, the distance between this electron and this electron is not wide like this. If it has shown this one, then I'll say it's another shell. So they are still removing these 2 from the same shell. Okay, they're still removing from the same shell. So if I see another one like this, I can tell that, oh, that's another shell. It's only 2 that's inside this one. Then there's, but because they said they still remove 2, and they never mentioned that this is the whole of the electron. If they have mentioned that the whole of the electron is this, I can predict the element is 6 now, of course, which is carbon. But in this case, they told me, they never gave me that information. So what I can say, what I can do is that I know the element is in group 4, comma, and since they remove 2 from the innermost shell, that means it's probably 8, and that will be 2. That means it's period 3, okay? That means the element is period 3. Period 3, group 4, and that will be 14. Whichever element that is in 14, I think is sulfur or something. That will be your answer. Now let's try to check another one. Let's try to check another one, predict the kind of element it is. Okay, where is that one? No, not this one. Okay. Now this. Okay. Now we want to predict. Although they wrote the element, but I want us to show that if we have this kind of graph, we can be able to predict the kind of element it is. Now in this case, they make it easy for you because they already put the arrow to show the points where the shells end. Okay, they already put the arrow to show the point where the shells end. Now look at it. For example, they said this is aluminum. Aluminum, does it have only 6 electrons in the outermost shell? In its shell? No, of course it has 13. So they cannot draw the 13 electrons. It's not possible. So they only draw some for you, then they ask you to infer. Now what I want to show is that, look at this chart. Look at the distance here. This one has already shown you that there is a change in shell there. Okay, there is a change in shell. So let's start with it. This, it will confuse you, so ignore that. So let's look at it. Let's try to predict. Now you see that the distance here to this place is not too subtle, it's not too brittle. Now from here you have long distance. That means this is the end of the outermost shell. 3 electrons in the outermost shell. I know it's in group 3. I'll write 3, comma. Now the next one is, it jumps up, then they start removing 1, 2, 3 from the same shell. If they remove 3 from a shell, it implies it has more than 3 at least, and there is no way you can have 3, 3. Have you ever seen that before? No, of course. So that means it means that shell must have gotten 8, and if it is must gotten 8, then probably the element has 2. So it's going to be like 2, 8, 3. So that's a way to predict the element. So I can predict that this element is most likely going to be in group 3, period 3, which is aluminum in this case. Okay, now let's try another one. Let's try the next one on top. Now you see the subtle, look at the change here. So that's where we're going. I'm not saying where the change ends, it's where it begins that you take note. Okay, now from they remove 1, they remove 2, then it jumps up. So that means it's in group 2, comma. Now they remove 1, 2, 3, 4. Definitely the element must have had more than 2. That will be 8, 2. That is 2, 8, 2. That will be magnesium. You get the idea? Now if you look at this chart, you see that the long breadth start from here, the long length start from here. Okay, start from the beginning. So that means it goes up after the remove one. So that means there is only one electron in the outermost shell. So it's probably going to be 1, comma. Then we have 1, 2, 3, 4, 5 removed. So probably it's going to be at least 8 electron. Then it will be 2, comma 8, comma 1. You see the idea? That's how you can predict the nature, the element in question without actually knowing it. By just looking at the chart of the ionization energy of that element, you may be able to predict correctly, at least to a great level of accuracy, that the element is something. But I want to highlight something. Okay, there's an assumption we are making here. At times you can have an element like 2, you can have something like 2, comma 8, comma 8, comma 1. You know that. So it is equally possible, if they did not tell me that this is sodium, this might also be the element. Okay, so that I'm saying that we are predicting. So because our rule, we explain that at the first one you remove 1, which is correct. The next one you remove 4, so probably it's going to be 8. What if the innermost one is also 8? Okay, but what I'm trying to say is that to a reasonable level of extent, they will not give you something that is beyond. So they will give you a range. They can say from 1 to 10 or something. But you use the idea I just give you to explain, to predict. You're going to get the correct answer. Most times they're going to give you something in that realm. Okay. So I think that's all about this one. Okay. Yeah, that reminds me. Let me put this in. Now this one is about what's this? The number of particles is basically on is related to the mass spectrum, okay? But it's somehow relating to isotope and all that. So let me just brush through this. Now to solve this kind of question, they said a 50p coin, leave all the p coin, you don't need all this information. A 50p coin has a mass of this and contains this present by mass of copper. Okay, you don't need all this 50p coin. Just scrap that. It doesn't have business with your calculation. It doesn't have effect on your calculation. It's just like I say, a black man has a mass of 8 grams. So will I start calculating a black man? No, of course. It doesn't have relationship. Now, um, now let's go to the next one. They said the mass of 8 grams. So mass is 8 grams, okay? Now they said contains 75%. So that means what is inside there, the whole of this is not a copper, okay? But only 75% of it is copper. So I'm going to calculate 75% of 0.8 of 8. 75 divided by 100 multiplied by 8, okay? So I don't know. You're going to get an answer. The answer you get is let me call it x. You can simplify that. I don't have my calculator here. Or let me bring it up to the calculator, okay? Oh, it's not. I have to manually do that. Okay. Um, let me bring out the marker. No, not yet. Now, what I want to do is 75%. 75. That will be 0.75. So multiply by 8. So I'll get 6. That means from this data, the mass of copper is just 6. Okay. From the question, it's just 6. So we have 6 grams of copper. Now they said calculate the number of atoms of copper in 50p coin. Okay, the number of atoms of copper in 50p coin. Now when you say the number of atoms of copper, they are talking about Avogadro constant, Avogadro number. Okay, remember from the basic chemistry that Avogadro number, which represents by n, is equal to 0. N is equal to 6.023 multiplied by 10 raised to the power of 23 particles. Okay, the particle in this question can be an atom, can be molecule, can be ion, can be particles. They can just call it particles. So it does not matter, still the same concept. Now, how do we calculate the number of atoms in it? There is a formula that joins all of them. Mole. Okay, mole has a number of formula. So don't think it's always mass over molar mass. No, mole can be mass over molar mass. I believe you should put this down. Mass over molar mass. Mole can be volume over molar volume. Mole can be number of particles, number of atoms, all over Avogadro number. In fact, there are so many units. It depends on where you're using the mole. Okay, it doesn't matter which concept, but it depends on which place you want to. If you're using the mole under volume, you're going to use this. If you're using the mole under mass, you're going to use this. If you're using the mole under Avogadro constant, like in this case, we're going to use this. But in this case, we have two conditions. We have mass and we have Avogadro constant. That means we are using two conditions. We're using the first one and the last one. So what I mean by that is we'll be using this. We'll be using this one. No, 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 not this one. Not this one. We're not using this. We're using this condition and we're using this condition. Since the two of them is what we have in, you can see we have mass and we have AR, then we're looking for the number of particles. So it is sensible to use the two. Now, let's try to use the two and see what we're going to do about that and how we're going to use it. Now, how we're going to use it is pretty easy. If I say X is equal to Y, they also said Z is equal to Y. Is it not correct to say that X is equal to Z? Mathematically, it's pretty correct because X and Z have the same answer. So it is possible to just say X and Z are the same. Okay, so that context is what I'm about to use here. Okay, so what I want to do is that, remember I said for my question that mole is equal to mass over molar mass. I equally say mole is equal to number of particles all over Avogadro constant. So since the two of them are mole-mole, I can say these two are equal to each other. Okay, it's the same context. So if I say that is equal, I can rewrite my formula as mass all over molar mass is equal to number of particles all over Avogadro constant. Now, why do I have to do this? Is because I have to look at my question and look at the points where the two of them meet together. Okay, now I can plug in my data now. The mass of copper that we calculated, remember, was not 8, it was 6. Remember, it's still on the screen of my calculator down here, 6. So I put 6 here, divided by the molar mass of copper is 63.5. They give me here 63.5 is equal to, now the number of particles is what I'm looking for. Let me call it MP. The Avogadro constant is 6.023 times 10 to the power of 23 particles. So you can solve for this to get your answer. I don't think that should be a problem. You can finish up that one. Okay. So this is the kind of question you can find too under this context. Okay, we'll stop here.